In this video, we're going to start discussing Boolean theorems and use how to apply them to simplify the logic of a digital circuit. So basically, like I said, by the end of the video, you'll be able to simplify a Boolean expression using Boolean theorems and Morgans theorems. You'll also be able to describe alternate gate representations and be able to design a circuit to solve a real-world problem. Those are our goals today. So Boolean theorems are rules that can help to simplify logic expressions and logic circuits. On your lecture notes, you're going to want to use the blank space on the first page to write down the Boolean theorems that we're going to discuss. There are 17 theorems total, so leave yourself some space. The first Boolean theorem is x and 0 equals 0, and all you really need to write down is this right here. X and 0 equals 0. And we can see with the picture accompanying this theorem that if you have an AND gate and one of the inputs is always low, the output will always be low. It doesn't really matter what the other input is. That's the first Boolean theorem. Theorem number 2, x and 1 will equal x. So if you have an AND gate where one of the inputs is always high, then the output really depends on what the other input is. If the other input is a 0, the output would be 0. If the other input is a 1, the output would be 1. So in this theorem, the output of this AND gate, or the output of this particular circuit, would depend on the second input if the first input is tied high. So that's number 2. Boolean theorem number 3. X and x equals x. And the way that we might represent this is if you had one input that was tied to both of the inputs to the AND gate. So you have one input x, which goes to both inputs of your AND gate. What would the output be? X and x is going to equal x. So if x is a 1, you'd have 1 and 1 equals 1. And if x is a 0, you'd have 0 and 0 equals 0. That's the third Boolean theorem. X and x equals x. Fourth theorem is x and not x equals 0. This is always going to be true no matter what x is, because if x is 0, then you'd have 0 and 1, which equals 0. And if x is 1, then that 1 would be inverted and you'd have 1 and 0, which equals 0. So as long as one of your inputs is going to be inverted, it doesn't really matter what's going to happen. You're always going to get a 0 out when you have x and not x. Theorem number 5, x or 0 equals x. So now we're switching over to OR gates. If one of your inputs to an OR gate is tied low, the output would be dependent on the other input. If the other input was a 1, you'd get a 1 out. If the other input was a 0, you'd get a 0 out. So Boolean theorem number 5, x or 0 equals x. Next we have x or 1 equals 1. This can be proven looking at the picture right above. If you have an OR gate where one input is always 1, it doesn't really matter what the other input is. The output's always going to be 1 because of how an OR gate works. So theorem number 6, x or 1 equals 1. Theorem number 7, x or x equals x. Basically, this is sort of the same idea that we discussed with the AND gate. If you have a single input x that's being fed to both inputs of an OR gate, the output is going to just be the same as that single input. And we can test that by saying 0 or 0, which would be 0, and 1 or 1, which would be 1. So theorem number 7, x or x equals x. Theorem number 8, x or not x equals 1. And with this particular theorem, we could see that no matter what x is, one of those inputs will always be 1. And if you have a 1 going into an OR gate, the output will be 1 regardless of the other input. So theorem number 8, x or not x equals 1. Now we're moving on to the commutative laws. And these are similar to the ones that you've seen in a prior math class, maybe in algebra or a pre-calculus class. The commutative laws say that x or y is equal to y or x. And x and y is equal to y and x. So when you're doing and, or when you're doing or, the order of your variables doesn't really matter. You can switch the order and you still have the same expression. So commutative laws are numbers 9 and 10. Next, we have the associative laws for laws 11 and 12. These are also very similar to what you've seen in a prior math class. If we have x or the quantity y or z, we can rewrite that to say the quantity x or y or z, or we can completely take away the parentheses. It all means the same thing because we only have one operation here. We only have or, and it doesn't matter which order you combine your terms. Same thing with and. If you look at law number 12, we have x and the quantity y and z, which is equal to the quantity x and y and z, which is equal to x and y and z without any parentheses. When you're doing just one operation, it doesn't really matter what comes first. Then we have the distributive laws, which is going to be 13a and 13b. These work the same way that you learned when you learned to distribute in algebra or pre-calculus. If you have x and the quantity y or z, that's equal to x and y or x and z. The x distributes the same way you would expect it to distribute in an algebra class. And then 13b is an implementation of FOIL, first, outside, inside, last. That also applies in Boolean algebra. So if you have two quantities, the first one being w or x and the second one being y or z, those two quantities are being ANDed together. That's equal to w and y, or x and y, or w and z, or x and z. Same application of FOIL that you've already seen before. So that's 13a and 13b. Next, we have theorems 14 and then what we call 15a and 15b. These ones do not have counterparts in ordinary algebra, so these theorems are not theorems you would have seen before. If you really need to prove to yourself that they're true, you can always make a truth table to see it. And this example here is the truth table for theorem 14. But theorem 14 says that x or x and y is always going to equal x. And this truth table kind of proves that idea by working those quantities out one by one and showing you that if x is a 1, the output is 1. If x is a 0, the output is 0, regardless of what y is. 15a and 15b, it's a little hard to see, but keep in mind this is an overbar over x. This says x or not x and y is equal to x or y. And this one right here also has an overbar. Not x or y is equal to not x. Not x or x and y is equal to not x or y. Make sure when you write these down in your notes, you have the overbar over these three places, right here, right here, right here. Make sure you have the overbar written down in your notes. That's important. You have to have that overbar. So that's the first 15 laws. 16 and 17 are De Morgan's Theorems. De Morgan's Theorems. And these are specific to NAND and NOR gates. Now, in order to simplify a NAND or a NOR expression, you have two things you're going to do. Break the bar, change the sign. Break the bar, change the sign. So if you have A and B going into a NAND gate, I can break the bar right here, change the AND to OR, and these equations are equivalent. These expressions are equivalent. So you can change a NAND gate into an OR expression where you invert not A and not B. You can also take the same thing with a NOR. You can break the bar right here and change the addition to multiplication, and that's an equivalent expression, which is very useful when you're simplifying a circuit. So 16 and 17, you're going to write down this one for number 16 and this one right here for number 17 for your 17 theorems that we're going to be using today. So why am I going over all of these theorems? Because they are tools that we are going to use to simplify a circuit. We always want to try to be most efficient with our time. So before building a circuit, one of the things that we're always going to do is simplify the expression for that circuit and make sure it's as simple as we can be before we build it. And these theorems allow us to simplify circuits. So let's do some practice of simplifying. Let's say that you have the expression y equals a and not b and d, or a and not b and not d. Now, we've already discussed how to create a circuit to implement that expression. And right now, that circuit would need a couple of inverters, it would need an OR gate, it would need 2, 3 input AND gates. Maybe we could make this circuit a little bit simpler. So we're going to use the Boolean theorems to do that. And what we're going to do is look through that list of theorems that you just wrote down and try to figure out how we might be able to apply them to manipulate this expression into something simpler. So the first thing you can notice is that both terms have an A and not B. You can factor that out just like you would factor numbers out of numbers or variables out of a regular algebraic equation. If you factor that out, here's what you would have next. Notice I could distribute this and end up right back to where I started. So these two expressions are equivalent. What I started with and this step, they're equivalent. So as you're applying the theorems, you're going to want to make sure you write down what theorem you're applying and when to validate your statement. So right here, we're going to use theorem 13 to factor out the common variables. Next, if you look at this piece right here, the D or not D, look at your theorems and you can see that theorem number 8 says that x or not x equals 1. Theorem number 8 uses x's, but an x can really be any other variable. So think of the D or not D as an x or not x. And theorem 8 tells us that that term is equivalent to 1. So then we have y equals a and not b and 1. This piece here gets replaced with a 1. Then you can look at theorem number 2 and see that x and 1 equals x. In this case, this piece, the a and not b, that's our x. So a and not b anded with 1 is just going to be a and not b. That's the application of theorem 2. And that will be the simplest that we could make this expression. So if you look at what we started with and you look at what we ended with, which circuit would take less time, energy, money, and materials to build? The second one, because you only need a NOT gate and one AND gate, that's it. This one is more complex. So using the Boolean theorems to simplify gives us a chance to cut out some of the work that we might ordinarily do. This is why we simplify. Let's look at another example. So we're going to simplify z equals the quantity not a or b and the quantity a or b. First thing that we're going to do is apply theorem 13b, where we're going to pretty much FOIL these two terms out. So we have first, outside, inside, last, which allows us to transform this expression into z equals not a and a, or not a and b, or b and a, or b and b. Next, we're going to look for anything that might cancel to either a 0 or a 1. If you look at the first term, not a and a will always be 0. That's theorem 4. Also, anything ANDed with itself is itself. That's theorem 3. So I can replace this term with a 0. I can replace this term with a b. And then I can say that 0 or anything is anything. That is theorem 5. Next, we can factor out b from what's left over using theorem 13. And then we have z is equal to b and the quantity, not a or 1. Next, we can look at theorems 2 and 6. And we can say that, first of all, looking at theorem 6, x or 1 is 1. We also know that x or not x is 1. That's theorem 8. So we can look at theorem 6 or theorem 8 to say that everything in the parentheses collapses out to be 1. No matter how you look at it, no matter which theorem you pick. Not a or 1 is going to be 1. It doesn't really matter what's in here. Anything or 1 is 1. So this ends up being z is equal to b and 1. Then if you look at theorem 2, anything and 1 is itself. So b and 1 would equal b. So this entire expression that we started with basically is a very complex way of saying that the output z will always be equal to whatever input b is and nothing else. So simplifying allows us to remove some of the work that we might do when building a circuit. Let's look at one more. We have simplify A and C and D, or not A and B and C and D. With this one here, you're going to start by looking for common terms. Both terms have a C and D, so factor that out. Next, this right here is where you're going to see the application of 15a. Go back to your list of theorems. Look at 15a. 15a says x or not x and y equals x and y. Imagine the a is the x, the b is the y. So we can use theorem 15a to replace that term that I've highlighted with just simply a or b. So when we replace that term, we end up with an expression, CD and the quantity A or B. And if we distribute that CD to both terms, that's what we end up with. And there's nothing much else you can do with this expression. You have 4 variables. You've factored out what you can factor out. There's not much else you can do with this expression. It doesn't get any simpler than this because you have so many variables. Now we're going to practice simplifying using some of the De Morgan's theorems. So let's say that you have the quantity C or, and then this is B NAND C. This is B and C going into an AND gate and then being inverted. That's a NAND. And we're going to simplify this using De Morgan's theorems. So first, you're going to take the B NAND C, you're going to break the bar and change the sign. The sign right now is multiplication, so you're going to make it addition. And then you're going to break the bar so that B and C get their own individual bars. That's an application of theorem 16, as we wrote down in our paper. Next, I'm going to rewrite this in just a different order, rewrite the terms, which I can do according to theorem 11. Remember, as long as we're doing the same operation, whether it's and or, it doesn't matter what comes first if I'm just doing or just doing and. In this case, I have 3 things that are ORed together. It doesn't matter what order they're in. I reorganized that so that it was clear to see that C or C becomes another theorem we can apply. If you look at theorem 8, it says that x or not x equals 1. So C or not C equals 1. That's theorem 8. And then we can use theorem 6. Theorem 6 says x or 1 equals x. Let the not be equal x. So that means that the final output would just be 1. When you're working these problems, it's very important with every step that you take to indicate the theorem in the margin to explain your reasoning or your choice. And it'll be very easy to go back later and remember why you did what you did if you write the theorem that you used in the margin. So as you're doing practice problems or homework problems or exam questions, the theorem you've selected to use should always be written in the margin, just like this example is showing. All right, let's do another one. Now this one is going to be a little bit more complicated, partially because we're starting off with a lot more going on. So we have the quantity A NAND B, and that's going to be ANDed with a quantity not A or B, and that's also ANDed with the quantity not B or B. And there's a number of places that you could start with this one. There's no right way to start. Just try to identify a place you can start. You could start by foiling all of this out. You could start by finding a theorem to simplify the not B or B. Or you could start by applying De Morgan's to break that apart. It's your choice where you choose to start. I decided to start by simplifying this last piece right here. Not B or B is equal to 1. And then 1 and anything is anything. So I'm using theorems 8 and 2 to make my first step. Theorem 8 says that I can replace this with a 1. Theorem 2 says the 1 and all of this stuff will just equal what's left over right here. That's my first step. Now, I cannot distribute this A NAND B with the not A and the B. I can't really distribute that because it wouldn't be helpful. It wouldn't get me anywhere that I want to go. So the next logical step would be to apply De Morgans to break apart the A NAND B right here. So this piece became this because of De Morgan's theorems. We can't really distribute a term when we have an overbar over more than one variable. Now that I've broken apart the first term, I can simply use FOIL, or Theorem 13, to simplify this a little bit further. So apply 13b and FOIL this expression. This is what you'll get next. First, outside, inside, last. Now I'm looking for groups of things that might eliminate or cancel. For example, we know that anything and itself is itself. So not A and not A is simply not A. We know that not B and B is simply 0. That's theorem 4. Theorem 3 is what you can use to make this step here. So we're getting a little bit simpler. And the next thing that I notice is that you have a common term. You have not A can be factored out of all 3 of these terms. If you factor the not A out of itself, you technically would have a 1 or B or not B. But we know 1 or anything is going to give you 1. We also know that B or not B is also going to give you 1. So this simplifies down to basically what's left inside the parentheses after you factor out the A is a 1. Any way that you decide to look at that, you get a 1. And so 1 and not A simply ends up being not A. And the theorems that you could use to say that are number 8 and number 2. So this is the solution for this one. A few more steps, but as long as you take it one step at a time, apply the theorem that you think will help you get to a simpler place. And if you start working these problems and you feel like you're not getting any simpler after 3 or 4 steps, stop, go back to the beginning, and try a different approach. Start from a different place than where you chose. And eventually you'll get to a point where the output is much simpler than the input. So here's another one. I want you to try to simplify this one on your own. So hit pause, look at all of the theorems we've discussed, try to simplify this one on your own. So for this one, what you're going to do first is recognize that you have a NAND gate here. And the 2 things going into your NAND gate are this term and this term. So when you break the bar, you're going to break the bar right here. You're going to change that sign to addition. And this is what you'll have next, Theorem 16. Take a very close look at where the overbars go. The A was originally inverted and it's still inverted. All I did was break the longer bar. It still stays across the whole group for the first term and the whole group for the second term. And this is not a double inversion. We're not going to cancel out the inversion over A because the bars are 2 different lengths. You can only perform a double inversion and cancel that out if the bars are the same length. So we can't do anything else with that right now. What we're going to have to do is apply De Morgans again by breaking this bar and breaking this bar and changing both of those signs. That's the next step. So change the OR to AND, break the bar. Notice that now I have a double inversion over A, and I have a double inversion over D. Those two bars are the same length. They only cover one thing. Now I can simplify those and take away the inversions altogether. And what's left is A and not C, or B, not B, and D. So keep in mind that we can only cancel out an inversion when both of the bars are the same length. Also keep in mind that when you have a whole group of things with an overbar, you can't break it apart unless you're doing De Morgans. You can't FOIL this out or add these together. There's really no other step but to break the bar and change the sign in order to simplify something like this. All right, take a look at the next circuit. It says to determine an expression for the circuit below and use De Morgan's theorems to simplify. So first, we're going to just determine the expression for the output. Notice that you have C, which is being inverted, and then going into a NAND gate with A and B. So coming out, just as a general expression for the output, this is what that would look like. We've got a NAND gate, so it means we have an overbar over A and B and not C. Now we have to break the bar here and here and change the sign. So if you break the bar and change the sign, that becomes not A or not B or not C. Here again is where you can perform a double inversion, and your final expression for the output is here. So we use these theorems to be able to simplify a circuit in order to maybe cut out some of the work. You know, we don't want to take 20 gates to build a circuit if 8 gates will do the job. So before we build a circuit, we often will check to simplify it using these theorems in order to save ourselves some time and to increase the efficiency of what we're trying to accomplish when we build a circuit. Next, we're going to talk about the universality of NAND gates. I have 3 circuits on the screen. Each one is made of only NAND gates. The first one has 1 input, 1 output. The second one has got 2 inputs and 1 output, and the third one also has 2 inputs and 1 output. If you were to figure out your algebraic expression for each one of these circuits, you're going to notice something interesting. If I were to take the concept of a NAND gate, which we talked about in our last video, remember we talked about the truth table for a NAND gate, and we did a waveform for the NAND gate. Remember that when you're looking at the truth table for a NAND gate, the output is always high unless both inputs are high. So if we look at this NAND gate right here, if A is a 0, that means we have a 0 and a 0 going into a NAND gate, and a 1 would come out. If A is a 1, that means we have a 1 and a 1 going into a NAND gate, and a 0 would come out. What does this truth table remind you of? The output is the inverse of the input. It's an inverter. If we were to look at the second circuit right here and apply the same logic, you would see that if 2 inputs are both low, you get a low out. If you have 1 low, 1 high, you get a low out. And if they're both high, you get a high out. What truth table does this remind you of? And lastly, if you make a truth table for this circuit and you were to work the logic through for each gate, you would see that the truth table for this circuit would look like this. That's the same truth table that we have for an OR gate. So the NAND gate is called a universal gate because you can make anything with only a NAND. You can create an inverter, you can create an AND, you can create an OR, which means you can then create every other type of gate that we're going to discuss in this class, because every other type of gate comes from the inverter, the AND, and the OR. So the NAND gate is considered a universal gate because of its ability to basically be wired to create anything you might need. So instead of using a combinational logic circuit where you have AND, OR, and NOT gates, you can just create that entire circuit using NANDs. And that just means that if you needed an inverter, you would replace your inverter with this circuit. If you needed an AND gate, you would replace your AND with this circuit. And if you needed an OR, you would replace your OR gate with this circuit, and it would work the exact same way. The same goes for NOR gates. NOR gates are also considered universal gates. If you wire your NOR gates in this orientation here, you'll create an OR gate. If you wire the NOR gates in this orientation here, you create an AND gate. And if you wire the NOR gate in this orientation here, you create an inverter, a NOT gate. So NAND and NOR are considered the universal gates because they can create literally everything else. If you didn't have any other chips on your shelf and the only thing you had was a NOR, you can create any circuit you want using only a NOR. And all you'd have to do is recreate the OR, the AND, or the NOT using these wiring diagrams. So here's a summary of what I just discussed, showing you the inverter with both ways, using an AND, using an OR. Here's the AND gate, using NANDs, using NORs. And then here's the OR gate, using NANDs and using NORs. So those are the universal gates because they can create our three basic ideas of AND, OR, and NOT. There will be times where you also might want to know how to have an alternate logic gate representation. So for example, let's say that you need to build a circuit with an AND gate and the only chip you have is blown and you can't use it anymore. What might be another way you can create an AND gate? So we just talked about one way using NAND and NOR. Another way to think about how to create an alternate logic gate is to think about the gate that you have, invert all the inputs and outputs, and then change the sign. So if this is an AND gate, change the sign to an OR gate, invert all the inputs and outputs, and you have an alternate representation to describe an AND gate. The same applies for an OR. If you need an alternate representation to represent an OR gate, you can invert the inputs, invert the output. So that means add a bubble if there's no bubble, or take away the bubble if there is a bubble. Invert the inputs, invert the outputs, and change the gate from AND to OR from OR to AND. So if I don't have an OR and I need to create one, I can create an OR by taking a NAND gate and inverting the inputs. I can create an AND gate by taking a NOR gate and inverting the inputs. You'll actually see this in one of your labs, I believe it's lab 5, where you're going to experiment with this concept. So these are called alternate logic gates because it's another way to represent AND and OR outside of the ways we've just discussed. Now we're going to start tying all these ideas together. We've talked about implementing a circuit. We've talked about building truth tables, alternate logic gates, simplification, Boolean theorems. We're going to start navigating towards tying all these together to actually build a circuit. And I'm going to show you a basic example today of how we take a real-world problem and solve it with a digital circuit. And the next video that I'm going to show you is going to go deeper into that concept for how we design a circuit. So here's today is just a basic example. So let's say that you are going to be designing a system for a car. The system is a safety system where it's supposed to turn on a warning light if the driver is present and the driver is not buckled while the car is on. So we have three conditions. The driver is present, the driver is not buckled, and the ignition switch is on. If all of those things are happening, we want to turn on a warning light because that means that that person may not be safe. So in the real world, how would we figure out if the driver is present? That would be a sensor in the seat of the car. So imagine that there's a sensor that can send a 0 or a 1, depending on whether or not the driver is present or not present. Also, how do we determine whether the driver is buckled or not? That's another sensor. So think about the sensor in your seatbelt buckle being able to send a 0 or a 1, depending on whether or not the person is buckled or not. And then we have the ignition, which also can have a sensor to sense whether the switch is turned on or off. So if we want to put all this together, what kind of circuit would we need to send the warning light? That's the question. So keep in mind that the warning light should go on if the driver is present and the driver is not buckled and the ignition is on. Those are our 3 conditions. So again, keep in mind that there's a sensor that sends a 1 if the driver is present. There's a seatbelt buckle that sends a 1 if the driver is buckled. And then there's a sensor that sends a 1 if the ignition is on. So these are all signals that are coming from sensors. So we have the driver. We got to know if the driver's buckled. We got to sense the ignition. And we got to send a warning. So what's our circuit going to look like? Basically, we'll need a 3-input AND gate where we're going to invert the signal for buckled. So if the driver is present, there'll be a 1 right here. If the driver is buckled, there would be a 1 right here, which would get inverted to a 0 here. If the driver is buckled, we don't need the warning light. So if there's a 0 right here, the AND gate would output a low and the light wouldn't sound. That's all good. But let's assume that the driver is not buckled. That means that there'd be a 0 going into the inverter and a 1 coming out. So if the driver's in the car, the driver's not buckled, and they've turned on the ignition, all 3 inputs to the AND gate would be high, the output would be high, a high output would then turn on the warning light. So that's a circuit that would implement the idea of a seatbelt alarm system in your vehicle. So if that's our circuit, now I want you to pause the video and come up with the truth table to describe how this circuit will work. You have 3 inputs. You have one of those inputs being inverted, and then they're going into an AND gate. So take a minute, pause the video, and complete the truth table for this circuit. And here's what the solution would look like. You have driver, buckled, and ignition. Those are your inputs. You're going to set up your truth table the way we've already discussed with the inputs counting up in binary. And we know there's only one time when the light should sound: if the driver's if the driver is present, not buckled, and the ignition the ignition switch is turned on. And that's when your warning light will sound. So that's a quick example of how we translate a real-world problem into a digital circuit that can solve that problem. The next video will go much deeper into the design process of how we design a circuit to answer or solve problems like this.